Hello students, today we are going to continue with the topic of the same chapter of work, energy and power. Now we did work and as well as a bit of energy we did. So today we are going to start with page number 340, potential energy. So potential energy is a very familiar topic. So whenever I ask anybody, so what is the formula of potential energy? Immediately they will say, sir, immediately they'll say potential energy is going to be equal to M into G into H. So this one, it is a very well known formula. You have been doing this one for many times. But remember, potential energy is a major topic. So potential energy has so many subdivisions. So before going to the subdivisions, let us first of all understand what is potential energy and then come to this one. Is this really a potential energy? Potential energy means the energy possessed by the body due to the position or the state of strain is called potential energy. That's what it's written here. I'm just reading from here. It is the energy due to the position. So that's the way in which we see potential energy stored in the body. So potential energy mgh is one variety of potential energy called gravitational potential energy. Gravitational potential energy means you take a body from the ground and you take it above the height against the gravity pull. Gravity is down. You take this body above the mass, above this elevation for a height h. So the body is standing here, then it has potential energy. So it is against the gravitational force. So it is stored as a potential energy here. So it is one of a part of this one. So don't say always potential energy means mgh is a formula. No. Gravitational potential energy has its formula as mgh. Then that means what are the other potential energies could be possible? Potential energy on a spring. So potential energy on on two masses, or maybe potential energy between two charges. Potential energy can be so many places it could be there. So basically potential energy it's coming again and again. What is potential energy? It is when you are there in one position and you change the position with the amount of force, but when you leave this one, it will come back to the original position. That means some force is constantly pulling it back. Now let me give an example of a spring here. A spring is attached with the body here. So it is just a normal body and spring is attached. Now you compel it by a force, external force, and pull it to this much distance. So what happens to here? The spring expands and the body is here. So this is the position here. The position which I am talking about here is because you gave an external force and the body is here. You leave this body here, what will happen? It will quickly come back to this position, or it will go beyond that, it will compress it and then start oscillating here also for some time. Now this is the original position. Now this is a changed position. This position where this body is lying here, it is stored as a potential energy because you have to do some work to bring it to this position for a distance x. So here the body is having an energy which is stored, that is called potential energy of the spring here. You leave this one, it will go back. So the position, in this position, the energy is stored in this one. Similarly, a body above the ground, in this position it is stored in this one. You leave this body, you just straight away goes back. So that is a kind of an place where you see a potential energy. It has an energy which is stored, so it has a potential of having an energy. That's the reason potential energy is stored. So you have anything like anything is done where you store an energy that is potential of giving that energy back. That is called potential energy. I hope you're able to get an idea about what is potential in the spring. Potential is the two masses of it is like that. So potential you have two charges. For example, two charges. One is a positive charge. Next one is a negative charge. What will happen? You leave these two charges. It will both come together and it will immediately attract. So what you do is a negative and positive charge. A negative charge you try to take it away and put it here. So you displace it for a distance x by a force. Then this charge, because of the position here, it is stored as a potential energy here. Potential energy between two charges. So potential energy could be not just of mgh. So we are coming to a bigger idea about it could be anywhere energy stored because of that initial position and the final position. The energy is stored because of its position. That is called potential energy. I hope you are able to get a bigger picture of what it is. So now go ahead and see in this book itself. Gravitational potential energy is mgh. You know this one. I'm not going to deal this one. Now we're going to do the main part of the next potential energy is potential energy in an ideal spring. Write down this topic. Potential energy in an spring. So that is the topic. Even if you don't write ideal also it's fine. Potential energy of a spring. So I was giving an example of spring already. So we'll try to do this one. So there is a three position we are going to draw. And this diagram is already there in the book itself. You can see this one. There is a spring here. And there is a body which is being kept here. So this is a mass. And this body is kept here. Then out of force you pull this body. And the spring expands. And the body has come to this position here. So you find here the body is gone from one point to another point. The body has gone to one point to another point because of an external force. This is an external force. You are pulling it out. So the x is the distance and f is this one. Now here I would like to make a very very important point. Please remember and please note this carefully. When you pull this one, the spring will exert an equal and opposite force called another F, called spring force is there. Like the frictional force, there's a spring force is there. The spring force will be opposite to the external force applied. This force is also called as a restoring force. Restoring force. What is restoring force? It will try its maximum to bring it back to the original position. Now you can ask, sir, you just leave it, what will happen? It will not stop here, it's going to go to this one. Okay, fine. It just compresses this one and this body is gone here also. Suppose if the body is gone here, you just leave it, it goes inside. There is another x dash from this one, from the mean position. There is another x dash, it is going inside. Even if it goes inside also, the restoring force will try to pull it outside. Even though this body is going inside, the restoring force will try to pull it outside. Wherever it is, it will try to push it away from the displacement here. So what does that mean? Now when you increase the distance here, more the distance, more will be the restoring force. So it becomes a kind of a proportionality constant. Because of the distance here, there is a restoring force. So you can write down when the spring is displaced and there is a change in the position, a restoring force acts on it to bring the spring back into its original position. restoring force F is proportional to displacement. Now restoring force is proportional to displacement, but it is a negative sign should be there. Why there is a negative sign? Look at this one. Now displacement has happened from here to here. This is the displacement, and restoring force is acting in the opposite direction. It is trying to happen. What is this force? This is then external force. This is an external force. Because of the external force, and restoring force is happening in the opposite direction because of the spring force. The spring force is called restoring force. So restoring force is always proportional to the negative of displacement. It is because it acts opposite. Displacement and force acts opposite. Look at this one. Restoring force is trying to restore this one back into this position, and displacement has happened in this direction. So it is always directly proportional. So the next line is F is equal to, you can make it as a proportional constant, you take it out, and then you can put equal to minus kx. So what is k? This k is called spring constant, where k is called spring constant. Very, very important equation. This is very important. K is going to be equal to F upon x, force upon displacement in a negative direction. So that is the way in which we define spring constant. So spring constant has a unit. It is a scalar quantity, but it depends upon the strength of a spring. Have you seen big trucks having a huge, big, thick spring which is there? Have you seen in the bikes where there's a huge, thick spring is there under the wheels, just above the wheel and the seat? That everyone will have its spring constant. K will be there. Have you seen a tiny spring which is there inside the pen also? That also have a spring constant. Everything will have its own value of spring constant. So spring constant means how much it can store energy in this one. How much it can again give it back. So that's what spring constant is. I hope you're able to understand what is spring constant. So look at this one. So we're going ahead down here. So F is proportional to minus x and F is equal to minus kx. Right? Now we are going to derive an expression. We're going to derive an expression for potential energy of a spring. So how it happens, what it does, we are going to derive it. Okay. So you can write down few things. Consider a spring which is stretched for a distance x. Due to an external force F dash is the external force. The restoring force acts opposite to the external force. External force capital F dash. Okay, the external force is F dash is equal to minus of F. What is this F? It is restoring force. We know this one already. These two are opposite in direction. I already told how it acts here. The restoring force. Now this is the restoring force. This is the F, and external force is here. Both of them are acting opposite in direction. So if this body is at rest here, then F external force is equal to restoring force. That's the reason it is in balanced position here. So that's what we are trying to say here, that restoring force is equal to minus F. So the external force is going to be equal to Kx then. Why there is no minus sign of Kx? Because the restoring force is going to be equal to minus Kx. So minus of minus, it will become, the external force is going to be equal to K into X. What is K? Spring constant. Alright. Now what we do is, in this one, as this body has been expanded here and in a other position it is there, away from the mean position. Earlier the body was here and it has gone to this position here and it is there at a distance of x. what you do is consider a very small displacement called dx. For this small displacement, how much work you need to do, you have to take, and then we can integrate between 0 to x position. Again, I am repeating, what we are going to do is, once the external force F dash acts on this body, we will see how much F dash is required, how much you will do the work for a small distance dx, not for the entire x, only for the short distance. Maybe this distance could be much more smaller. Then we'll see how it's going to be. Take down. Consider a small distance dx on which the external force acts. Work done for dx, for the distance dx, you can say distance dx, dw is going to be equal to f dash into dx. We know this one, f dash into dx. Maybe you can put it cos theta also. F dash into dx, fs cos theta, and both of them acts in the same direction. This also acts in the same direction. So since theta is going to be equal to 0, so it's going to be f dash into dx. That is dw. Now this is a small distance. For the small distance, you got the small work done. For the total distance, what you need to do? Integrate on both sides. Write on the next line. For the total work done from 0 to x, integrate on both sides. So integration of dw is going to be equal to integration of f dash dx 0 to x. Before we go ahead and do the integration, look at this f dash. We already know what is f dash is. Minus, it is going to be plus kx. Put this one here. So integration of 0 to x, kx into dx. That is integration of dw. Now as you integrate, you know this one very well. Integration of dw will become w here. And k is a constant. It can be outside. So integration of x dx only will be there, 0 to x. Then what is x dx? X into dx. We already know this is a power of 1. So whenever you integrate the power of 1, so what will happen? You add to a power of 1, you add another 1, n plus 1 upon n plus 1. So it is 1 plus 1. It is going to be equal to x square by 2. So you know this one. So it becomes k times of, you need to put this as a bracket, x square by 2, 0 to x. That's the way we usually put. So w is equal to, we have already learned this integration so well. I am sure that you will still remember this one. So 2 is taken outside. So it's going to be x square minus 0, because x you need to put one time, and then 0 you put the next time with the minus sign. So you get here finally k x square, and this is half w. This is called potential energy. The w, the work, w is the potential energy of spring. You can call it as u is going to be equal to half kx square. This is the final expression. The work done is the energy stored in the as a potential energy in the spring. It is called as u. U is going to be equal to half k into x square. What is x? Displacement. What is k? It is the spring constant. What is u? It is the potential energy. So you get this derivation, entire derivation here. The derivation is here. Have a look on this. This derivation is the one which we derived right now. Okay. Now once the derivation is over, you can also do it little graphically also. You can write down graphical method. It is called graphical method of potential energy of spring. So draw a graph which is the potential energy here, and you can say the distance here, right? So it is not potential energy, it can say, I'm sorry, it is force and the distance here. You can say displacement here, right? So what happens, force and displacement is directly proportional. You know this one, force and displacement is directly proportional, external force. This is not the internal force. Internal force is the restoring force. We are talking about external force here. So he talks about value where will be like this. The graph will be proportional graph. It will be a straight line. Now what you do is you try to cover this one, and we are trying to see what is going to be the area of this one. It is O here. Maybe it is A and this is B. So work done in a spring is going to be equal to area of the graph OA. So what is the area of the graph here? Half into base into height. This is the force. That's what it happens, base into height. That's a force here, and that's going to be work done. Now we already know F is nothing but F is going to be equal to K into X. We know this one. Put this value is equal to K into X here. So that's going to be equal to half into K into X square. That's W. So you can call it as U as half Kx square. So this is another way of doing graphically. Graphically also same formula will come, because we always know work done is going to be equal to area of the thing enclosed. We already saw this one in the previous one. If there is a variable force is given there, we saw this one like this. So what did we do with this one? We took the area of this one. Work done is going to be equal to area. That same thing we have applied here also here. Work done is going to be equal to area enclosed because of the force and displacement. So you get here finally this expression. So that's what it's given here. So you get this formula and then you get this one, right? So one more, just a note of it. The conservative force, the force is going to be equal to minus of du by dx, that is minus of potential energy. The potential energy, increase in the potential energy, okay, and it is the negative work done. It is actually a negative work done upon dx. It is called potential gradient. Du by dx is potential gradient. Alright, work done is going to be equal to minus of potential energy. Whenever you do a work done, it is stored as a negative of thing. So that's what the potential gradient is. Now we'll move forward to the next part of it, called principle of conservation of energy. Principle of conservation of energy. So this is a very simple thing. You already learned this one in the lower classes. Energy can neither be created nor be destroyed. One form of energy has to be transformed to the another form. That means the total amount of energy in the universe remains constant. The entire universe, all the galaxies, everything, God has put one form of energy. Maybe trillions and trillions of joules of energy is stored. And that energy only is a constant value, and we are just changing one energy to another energy. Energy can neither be created nor be destroyed. That means you cannot create energy. If you create energy, you will become God. God has put energy, and that's energy. That's it. What we are doing it? We are just converting energy. And you cannot destroy energy. You cannot change energy. You can only change energy from one form to another form. So the principle of conservation of energy has an example of free fall of a body under gravity. So please write down principle of conservation of energy. Energy can neither be created. You write this one, and then we're going to see how this energy conservation works in different formats. We are going to just take a simple example of potential energy and kinetic energy, how it works. I think you've studied this one in grade 9 or maybe grade 10. It's quite a simple one, but we'll quickly run through it. And it's quite an easy one, but it's also important to take a look on this. So free fall of a body under gravity. Please write down free fall of a body under gravity. There is a position A above the ground. So this body is having a height here as h. Now this body has come to this point. There's a position B, and finally the body is coming here to the position C. This one is already you've done. So you drop a body here and it has a velocity v here, right? And finally it crashes down here at C and lands up here. So all the three positions A, B and C, we are going to see the energy stored. Okay, at A, what happens? At A, what is the potential energy? Is equal to mgh. And what is the kinetic energy? Is equal to 0. What is the total energy? Potential energy plus kinetic energy is equal to mgh plus 0. It is going to be equal to mgh. This is equation number 1. Next one is at B. So when it is at B, what happens is the body is already dropped down here and it has traveled a distance of x. So what is the remaining distance which is going to be there? The remaining distance is going to be equal to height minus x. So that's the remaining distance which is there. Still it is above the ground. So what is the potential energy? It is going to be equal to m into g into, it is above the ground, it is height minus x. So it's already like this. Now what is the kinetic energy? We need to see it is going to be equal to half m v square. What is this v? It is going to be equal to v square minus u square is equal to 2gx. How much is x? The distance which is traveled from here to here. So v square is equal to 2gx. Substitute this v square over there. So kinetic energy is going to be equal to half into m into 2gx. It gets cancelled out. 2gx is going to be the kinetic energy. So what is the total energy here? Potential energy is here. Kinetic energy is here. Add both of them. Kinetic energy plus potential energy is equal to mg h minus x plus this becomes mgx. So it becomes finally mgh itself. This is at B. At B also it becomes the same. Equation number 2. First also, there also the energy is same. Here kinetic energy was something. Kinetic energy was this much. And potential energy was this one already. So both together, put together, it is same energy. At C, what happens? At C, kinetic energy is going to be equal to half m v square. Potential energy is 0 because the height becomes 0. Potential is 0. So what is the v? V square is going to be equal to 2gh. So putting together, kinetic energy is going to be equal to half into m into 2gh. So it is going to be mgh itself. So total energy is going to be equal to potential energy plus kinetic energy. It is equal to 0 plus mgh. It is going to be equal to mgh itself. So you know this one already. That's the total energy. This is equation number 3. So all the three places, mgh, first position also, top also mgh, here also mgh total energy, here also total energy is mgh. So finally what is concluding? You combine all the force, energy will be always equal. So you cannot change the energy. Wherever it is there, the energy will be constant. So when you add together, it will be the same. So there is a graph. This graph already you would have also noted this graph. The graph is height, the height which you are there, and the energy. So what happens when it is at the lowermost point? At the lowermost point, potential energy is 0, and the height, as the height increases, the energy increases. So this is potential energy graph. Now what happens to the kinetic energy? The kinetic energy happens in the other way around. So it starts from here and it finally drops down. This is kinetic energy. Kinetic energy will be from top to the bottom, it will come. As that height increases, the topmost point, the kinetic energy will be 0. So kinetic energy is equal to 0 at the topmost point. And here potential energy is maximum. Potential energy is maximum at the topmost point. Look at this one, there's a thing. And total energy will be like this. A thick line can be drawn like this. This is total energy. Kinetic energy plus potential energy. You know this one? The graph is also already here. You have studied this one earlier also. Please note down this graph. Right? So moving to the next part of it. Similarly, a graph can be drawn for the spring also. For example, if you have a spring which is oscillating constantly, there is a spring which is oscillating constantly with this body here. It goes up here and it is again coming back here, and there is mean position 0, x is equal to 0 here, and it goes for x here and it comes for another x here. It just oscillates here up and down. Then the energy comes like this, parabola. Now the energy is, please write down, it is in between. You need to put the energy here. Draw this diagram. Displacement, first part of displacement is here. That means it is going from here to here. That's what the potential energy increases. It increases and comes here. And you leave it back. Alright, now the kinetic energy, it goes from the top to this one. It stops here. The energy, kinetic energy is maximum in the mean position. It goes, the kinetic energy is very much higher in the middle position. And that's what it is in the top. It comes here like this. And the next part, it is in this position from here to here. So it comes like this and it also goes like this. So this is the total energy. The top line is the total energy, right? So half kx square is going to be the total energy all the time. So that is the kind of an energy conservation. This one, you need to explain this one also, how it becomes. Alright. So the last bit of it is here, the different forms of energy. You know, there's a heat energy, internal energy, electrical energy, chemical energy. These are all things you would have studied in the lower classes. I'm not going to the details of this. And transformation of energy also, you know. Energy can be transformed. So you have done very clearly so many examples you would have studied in the lower classes. So this will not come much in this one because you have done so much in the lower classes. So one important note I would like to take it out is, write down mass energy equivalence. Page number 344, mass energy equivalence. So for a long time people have been thinking mass and energy is different. Mass has nothing to do with energy. So after some time, when Einstein came, he and other people, they all found out these two has an interlink. Let me give an example. You take a small wooden piece. There's a wooden piece, maybe there's a duster is there in the one school, there is a wooden piece. You burn it. You put in a flame. This duster the mass was 100 grams. After you put some lit on some fire, then the duster will start burning itself. You need not keep on putting flames. But duster will start burning, and finally you will get some residues is there. Finally there is a heap of ashes there. The big mass is reduced to this one. Now finally you take this one and see, maybe it is 10 grams. From 100 grams it has become 10 grams now. How much the difference is masses? The difference in mass is 90 grams. The question happens, where this 90 grams went? What happened to the change in mass? The change in mass has happened in a form of a flame. The flame went off. Heat energy went off. And maybe it could have put some sound also. Or radiation has happened. So all things. Now there is a change in mass. Okay. So energy, how it happened is, the mass has been converted to energy now. So mass and energy means mass can be converted to energy also. Don't think only energy can be converted to energy. So now they are putting another part of it. A wood can be reduced into small. The mass is now converted to energy. Petrol, mass is there. It is just now fueled. Finally you don't get anything. Finally everything is now burnt. The mass is converted to energy. So energy can be converted like delta M, the change in mass. The mass which is now hidden, it is now just gone away, vanished, is 90 grams, into velocity of light the whole square. C is velocity of light. What is velocity of light? 3 into 10 to the power of 8 meter per second. I don't know what kind of relation they found in mass and velocity of light, but it happens that way. It happens that way. So if you look at 90 grams, 0.9 0.09 into 3.3 into 10 to the power of 8 the whole square. You multiply these two things. When you multiply, you will get a big number, 10 to the power of maybe 15 or something you get here. That much of joules is the energy which has gone out. This much energy you can calculate when mass is now burnt into the residue. I hope you are able to make a kind of a clear idea about there is definitely a mass energy equivalence, mass and energy, and it is multiplied by velocity of light the whole square. How it came, this is quite a mystery. People predicted, it is still a hypothesis, but it works. That's the way it is. E is equal to mc square. It is the speed of light in vacuum. That is now it is done, and enormous amount of energy is obtained. The relative indicates that enormous amount of energy is obtained by the complete conversion of very small amount of mass. A small amount of mass, 90 grams, and it is giving such a great amount of joules of energy. Look at this one. So it is quite a big thing. Last part today, before we close, the definition of power. Very well known thing, just you need to write. Power is the rate of doing work. Work divided by time. Please write down the formula. Power is going to be equal to work upon time. P is equal to W upon T. Right? So power is also can be instantaneous. At one immediate point, power is going to be equal to dW upon dt. Now remember, always we need to take in terms of a differential quantity where delta t dt is very very small. At the shortest time, this is going to be the value. Right? Now we know dW is going to be equal to force into dx. Alright. So we know this formula. So for any time, force into displacement. So take out this one, power is going to be equal to F into dx upon dt. So what is dx upon dt? The rate of change of distance, displacement is going to be equal to velocity. So power is going to be equal to F into V. The force into velocity. It is called velocity. So that comes into play here, F upon F into V. Now power is a scalar quantity. Power is a scalar quantity. Force is a vector quantity. V is also a vector quantity. So it becomes as a dot product here. So Fv cos theta it would become. That is called power. So theta could be equal to 0 degrees, 180 degrees, and all things. It depends upon force and velocity how it moves. Alright. So what is the SI unit of power? SI unit of power is going to be equal to watt. So W is small w you need to put. Watt is the SI unit. And also you have a horsepower is also another unit of power. So 1 horsepower is going to be equal to 46 watts. Know this one. And what is 1 watt is going to be equal to 1 joule upon 1 second. So if you want to convert 1 watt into the CJ system, it is 10 to the power of 7 erg per second. So that's also another thing. So with this we close. This is all a known fact, so we have already discussed this one. It's all here. So please write down this. If you are taking this one, it is already given as a vector quantity here. Please write down as a vector quantity. That will be easy. Vector quantity, so it's a dot product here. And look at this one, page number 345. 345. These all things is given here. Units and dimensions of power. Look at this one. Dimensions comes every time. So dimension is here also. So it is MLT, ML square T minus 3. The one which we studied before. It is coming now only every time. Okay. Alright children. Thank you. We have already finished this much power. We have left out with one very important topic called collisions that we will do tomorrow. Thank you.